welcome to this deep dive. You've pointed us towards some really interesting stuff this time. Circle geometry, specifically tangents, those lines that just, kiss the circle edge, and what happens when chords cross paths.
Exactly. And we've got a great set of materials you sent over, some fundamental definitions, the core theorems with their proofs laid out, and quite a few solved examples showing it all in action.
Right. So our mission today is to really dig into these concepts. We want to pull out the essential bits about tangents and intersecting chords, get a feel for how they work, the logic behind them.
And hopefully uncover some neat connections, like what happens with tangents from the same point, or that constant product you find with intersecting chords. It's pretty elegant stuff.
Okay, let's jump in. Where do we start?
Let's start with the basics. Lines interacting with a circle. We've got two main types here, seconds and tangents.
Okay, seconds and tangents. So a second, looking at the diagrams here, that's a line like CD, right? It just cuts straight through the circle at two different points.
Precisely. 2 points of intersection. Think of it slicing through.
But a tangent, like EF in the diagram,
Yeah.
that's different. It just touches the circle barely at one single point.
Exactly. Just 1 point of contact. It grazes the edge and moves on.
And that single point P, in this case, that's the point of contact. That sounds important.
It is. It's key. And it leads us right into our first major theorem, Theorem 10, which describes the relationship between this tangent and the radius drawn to that point.
Ah, okay. Theorem 10. The tangent at any point of a circle and the radius through this point are perpendicular to each other. Perpendicular. 90 degrees.
Always. Absolutely fundamental. So picture your circle, center O. Draw a tangent line, AB touching at point P. Now draw the radius from the center O to that point. See?
That line segment, OP.
Yes, OP. Theorem 10 guarantees that OK and AB meet at a right angle. They're perpendicular.
And the proof you shared, it's quite clever. It says, take any other point on the tangent line, say Q, not the contact point P.
Right. Connect that point Q back to the center O.
Because Q is in P must be outside the circle.
Right. Exactly. Any point on the tangent other than P itself is outside the circle boundary.
So the line OQ has to be longer than the radius OP.
It has to be. And this is where that little remember note comes in handy. The shortest distance from a point, the center O, to a line the tangent AB is always the perpendicular distance.
I see. Since OP is the shortest possible line from O to the tangent AB, it must be the perpendicular one.
Precisely. It's a neat bit of logic.
That makes sense.
Yeah.
So this perpendicular rule, it tells us something about how many tangents we can draw from different places.
It does, yeah. 3 key scenarios emerge directly from this.
Okay, what are they?
First, if you pick a point inside the circle, you can't draw any tangents from there.
Right. Any line you draw is going to cut through twice eventually. It'll be a second.
Exactly. Second, if your point is exactly on the circle's circumference.
Like point P was.
Yes. Then you can draw one and only one tangent through that point. It's unique.
Okay. 1 point on the circle, 1 tangent. Makes sense.
And third, if your point is outside the circle, an external point.
Then you can draw.
Exactly 2 tangents from that single external point to the circle. They'll touch the circle at 2 different points of contact.
2 distinct tangents reaching out. And that leads to a corollary, right? Some useful facts about these 2 tangents from the same external point.
Yes, very useful. Let's call the external point P again, and the points where the 2 tangents touch the circle A and B. So we have tangents PA and PB.
Okay.
The corollary tells us 3 things. 1, the lengths PA and PB are always equal.
Oh, interesting. The distance from the external point to the contact point is the same for both tangents.
Always. 2, they subtend equal angles back at the center O. So angle AOP is equal to angle BOP.
So those central angles are mirror images.
Exactly.
Yeah.
And 3, they're equally inclined to the line connecting the external point P to the center O, meaning angle APO equals angle BPO.
So that line PO perfectly splits the angle between the 2 tangents. Symmetry all around.
It is, and it all comes down to congruent triangles.
Right. The proof mentions triangles AOP and BOP.
Yeah. Look, OA and OB are radii, so they're equal. Angles OAP and OBP are both 90 degrees because radius is perpendicular to tangent.
Oh, we just established that.
And the line OP is common to both triangles. It's a hypotenuse for both right-angled triangles.
So we have a right angle, the hypotenuse, and another side, RHS congruence.
Exactly, right? Hypotenuse side. Since triangles AOP and BOP are congruent, all their corresponding parts must be equal. That includes the tangent lengths PA and PB and those angles we just talked about.
Got it. Very neat. Okay, so that covers tangents from one point. What about when we have 2 circles interacting? Theorem 11 deals with touching circles.
It does. It covers what happens when two circles touch each other, either externally, like two bubbles just meeting, or internally, where one is sort of nested inside the other.
Okay.
The theorem states that if two circles touch, their point of contact always lies on the straight line that goes through both of their centers.
Always on the line connecting the centers. Let's break that down. Case 1, external touch. Two circles, centers A and B, touching at point P on the outside.
Imagine drawing a common tangent line, PQ, that touches both circles right there at P.
Okay, a line skimming both at P.
We know the radius AP is perpendicular to PQ, so angle APQ is 90 degrees.
Right, Theorem 10 again.
And similarly, radius BP is also perpendicular to the same line, PQ, at the same point P. So angle BPQ is also 90 degrees.
So if APQ is 90 and BPQ is 90 and they're adjacent.
Then angle APB, the angle formed by A, P, and B, must be 90 plus 90 equals 180 degrees.
A straight line. So AP and B must be collinear. They lie on the same line.
Exactly. Now, case 2, internal touch. One circle inside the other, touching at P centers A and B again.
Okay.
Same logic, really. Draw that common tangent PQ at P. Radius AP of the larger circle is perpendicular to PQ. Radius BP of the smaller circle extended to P is also perpendicular to PQ at the same point P.
You can only have one line perpendicular to another at a single point?
Precisely. So AP and BP must lie along the same line. Again, the centers A and B and the point of contact P are collinear.
Makes sense. And there's a handy note about the distance between the centers. D, based on the radii R1 and R2.
Yeah, quick formulas. For external touching, the distance between centers is just the sum of the radii. D equals R1 plus R2.
Like laying them end to end.
Right. For internal touching, it's the absolute difference. D equals R1, R2.
Okay. And there's another point here about parallel tangents. If you have two tangents, A, B, and CD, that are parallel, and they touch the circle at P and Q.
Then the line segment PQ connecting those contact points is always a diameter. It goes straight through the center.
Got it. And concentric circles. Just circles sharing the same center.
Exactly. Like a bullseye target.
Okay, theory established. Let's see how this plays out in the solved examples. Example 1. A circle inscribed in a right-angled triangle.
Right. We have triangle PQR, right angled at Q. PQ is 24 centimeters. QR is 7 centimeters. We need the radius of the circle tucked inside, touching all three sides.
First step in the solution is finding the hypotenuse PR using Pythagoras. 24 squared plus 7 squared. Square root gives 25 centimeters.
Correct. Now, let the radius of the inscribed circle be x. Let it touch sides PQ, QR, PR at points A, B, C, respectively.
Right.
Think about the corners as external points. From Q, tangents QA and QB must be equal. In fact, QAOB forms a square, so QAB, QP, all x, the radius.
Ah, right. So if QA is x, then PA on the side PQ must be 24 minus x.
Yes, and similarly, RB on side QR is 7 minus x.
Now we use that property again. Tangents from an external point are equal, so from P, the tangent PC must equal PA, which is 24x.
Exactly. And from R, tangent RC must equal RB, which is 7x.
And the whole side PR is just PC plus RC.
So we set up the equation PR, PC plus RC. We know PR is 25, so 25 and onto 34x.
Plus 7x. Okay, 25 was 31, 2x. Rearranging, 2x equals 6 all is an x is 3 centimeters. The radius is 3.
That's it. Using that tangent property neatly solves it.
Clever. Okay, example 2. Tangents and angles. Points A, B, C on a circle. Tangent at C meets BA extended at T. We're given angle ATC is 36 degrees and angle ACT equals 48 degrees. Find angle BOA at the center.
A bit more angle chasing here. First, use radius tangent perpendicularity. If O is the center, OC is perpendicular to the tangent at C. So angle OCT equals 90 degrees.
And we know ACT is 48 degrees, so angle OCA must be 90 minus 48, 42 degrees.
Good. Now, triangle OAC is isosceles because OA and OC are both radii.
So angle OAC must also be 42 degrees, same as OCO.
Right. Next, use the exterior angle theorem on triangle ACT that exterior angle CAB is the sum of the interior opposites ATC and ACT.
So angle CAB equals 36 degrees plus 48 degrees, 84 degrees.
Yep. Now we know the whole angle CAB is 84 degrees and the part OAC is 42 degrees. So the other part, angle OAB, must be 84 minus 42, which is 42 degrees.
Okay.
And triangle OAB is also isosceles. OA equals OB radii. So angle OBA must equal angle OAB, which is 42 degrees.
So in triangle OBA, we have angles 42 degrees and 42 degrees. The sum is 180 degrees. So the last angle BOA must be 180, 42, 42.
Which equals 96 degrees. That's our answer.
Nice step-by-step deduction. Example 3 looks tricky. 3 touching circles.
Yeah, bit more algebra. We have circles, centers P and Q, radii 9 centimeters and 2 centimeters. Distance PQ equals 17 centimeters. Third circle, center R, radius X, touches the other two external. And crucially, angle PRQ equals 90 degrees. Find x.
Okay, the key is that distance between centers of externally touching circles equals the sum of their radii.
Exactly. So distance PR between the 9 centimeter radius circle and the x centimeter radius circle is 9 plus x.
And distance QR between the 2 centimeter and x centimeter radius circles is 2 plus x.
And P, R, Q form a right angle triangle with the right angle at RPQ as the hypotenuse.
So Pythagoras, PR plus QR radii equals PQQ.
Substitute what we know. 9 plus x plus 2 plus x equals 17 centimeter.
Okay, time to expand. 81 plus 18x plus xa5 plus 4 plus 4x plus xx equals 9.
Combine terms. 2xx plus 22x plus 85 equals 289.
Subtract 289. 2xs plus 22 by 204 equals every.
Now we solve this quadratic. Factoring. Need two numbers that multiply to next 102 and add to 11. 17 and neg up is 6.
Perfect. So x plus 17 by 6 equals airy.
Which gives x is 17 or x is 6. Radius can't be negative.
So x must be 6 centimeters. Great. Example 4. Direct common tangent. Two circles, radii 25 centimeters and 9 centimeters, touching externally. Find the tangent length.
Okay, visualize the two circles touching. The direct common tangent skims along one side. The trick is to draw a line parallel to the tangent, starting from the center of the smaller circle, running to the radius of the larger circle.
That forms a right angle triangle.
Yes. The hypotenuse is the distance between the centers. Since they touch externally, it's 25 plus 9 equals 34 centimeters.
Okay.
One leg of the right triangle is the difference in the radii. 25, 9 equals 16 centimeter.
And the other leg is the length of the direct common tangent we want.
Exactly. So Pythagoras again, tangent length, plus 16 1 and nose equals 34 meter.
Tangent length plus 256 equals 1156.
Subtract 256, tangent length, 100.
Square root of 900 is 30, so the tangent is 30 centimeters long.
Correct. Now, example 5 is similar, but for a transverse common tangent.
Transverse, that's the one that crosses between the circles, right?
Yes. Circles have radii 6 centimeters and 2 centimeters. Centers are 10 centimeters apart.
The construction here also makes a right triangle.
It does. Again, the hypotenuse is the distance between centers, which is 10 centimeters.
But this time, one leg is the sum of the radii. 6 plus 2 equals 8 centimeters.
That's the key difference for the transverse case. The other leg is the tangent length.
So tangent length plus 8 modulus 8, because
Tangent length plus 64 for 100.
Subtract 64. Tangent length 36.
Square root gives 6 centimeters for the transverse tangent length.
Got it. Okay, last example, number 6. Back to angles and tangents. We have triangle PQR with PQQR. Angle RQP equals 68 degrees. BC and QC are tangents to a circle with center O. Calculate angle QOP and angle QCP.
Two parts. First, angle QOP. Since PQ2R, triangle PQR is isosceles.
So angles QPR and QRP are equal. They must be 180, 68, 2, and 112, 2 equals 56 degrees each.
That's correct. Now, remember the rule. Angle at the center is twice the angle at the circumference subtended by the same arc. Angle QOP is at the center, subtended by arc QP. Angle QRP is at the circumference, subtended by the same arc QP.
So angle QOP, consider the quadrilateral POQC.
Hmm.
Consider the quadrilateral POQC. Okay, the shape formed by the center and the two contact points in the external point. See, wait, the external point is Q in the diagram. Oh, I see. PC and QC are tangents from point C to a circle passing through PQR with center O. Let me reread. PQQR, RQP 68 degrees. PC and QC are tangents to a circle with center O. Okay, so C is the external point here. We need angle QCP. Right, sorry, C is the external point. We know radius is perpendicular to tangents. So OP is perpendicular to QC, angle OPC equals 90 degrees, and OQ is perpendicular to QC, angle OQC equals 90 degrees. So in quadrilateral POQC, we know three angles. OPC equals 90 degrees, OQC equals 90 degrees, and we just found QOP, it was 112 degrees.
And the angles in a quadrilateral add up to 360 degrees.
So angle QCP is 68 degrees, 90 degrees, 90 degrees, 112 degrees.
It often works out neatly like that. So those examples show the theorems in action. Now, let's switch gears slightly to intersecting chords with Theorem 12. Okay, Theorem 12. If two chords of a circle intersect internally or externally, then the product of the lengths of their segments is equal.
A really powerful rule. Let's take the internal case first. Chords AB and CD cross inside the circle at point P.
The theorem says PA times PB equals PC times PD.
Exactly. The product of the segments of one chord equals the product of the segments of the other.
And why is that? The proof uses similar triangles.
Yes, triangles APC and BPD. Look at the angles. Angle A and angle D both subtend arc CB, so they're equal.
Angles in the same segment.
Right, and angle C and angle B both subtend arc AD, so they're also equal.
So the triangles are similar by angle AA.
Which means corresponding sides are proportional. PAPD equals PCTB. Cross multiply and you get PAS. PB equals PC, it's PD.
Neat. And it works even if they intersect outside the circle. Say chords AD and CD are extended to meet at point P outside.
Still works. The rule is the same. PAS, PB equals PC, APD. Here, PA is the whole length from P to the far intersection point A, and PD is the length from P to the near intersection point B, same for PCD.
The proof is similar triangles again, PC and PDB.
Yes. Angle P is common to both. And the exterior angle of a cyclic quad equals the interior opposite. So angle A equals angle PDB.
Oh, right.
And angle C equals angle PBD for the same reason. So again, the triangles are similar by AA.
Giving PAPD equals PCPD, which cross-multiplies to PA, APB equals PCAPD. Amazing that the same formula holds.
It's a very consistent property. Now, Theorem 13 relates a tangent and a chord. It's often called the alternate segment theorem.
Okay. The angle between a tangent and a chord through the point of contact is equal to an angle in the alternate segment.
Let's picture it. Tangent PQ touches the circle at A. Chord AB is drawn from A.
Okay.
The theorem says the angle between the tangent and the chord, say angle BAQ, is equal to the angle made by the chord at any point C on the other side of the circle, the alternate segment, so angle ACB.
So BAQ equals ACB. And what about the angle on the other side of the chord, angle BAP?
That equals the angle in its alternate segment, say angle ADB, where D is on the minor arc.
Okay, how does that work? The proof involves drawing a diameter.
Yeah, draw diameter AOR through the contact point A. Join RB. Angle ABR is 90 degrees, angle in a semicircle.
Right.
So in triangle ABR, angle ARB plus angle RAB equals 90 degrees. Also, we know the radius OA is perpendicular to tangent PQ, so angle OAQ equals 90 degrees. That means angle ARB plus angle BAQ equals 90 degrees.
So both ARB plus RAB and RR plus BAQ equal 90.
Which means angle ARB must equal angle BAQ.
Okay.
And we also know angles in the same segment are equal. ARB and ACB both subtend arc AB, so ARB must equal ACB.
So if ARB equals BAQ and ARB is similar, it's a really useful theorem for finding angles.
Definitely seems powerful. Okay, one last theorem, Theorem 14, secant and tangent intersecting externally.
Right. Point P outside the circle. Draw a second line from P that cuts the circle at A and B, PBA. Draw a tangent from P that touches the circle at T, PT.
Okay.
The theorem states PAEPB equals PT city. The product of the second segments from the external point equals the square of the tangent length from that same point.
PA times PB equals PT squared. How's this proved?
Right.
More similar triangles. You guessed it. Triangles PT and PTB.
Let's see. Angle P is common to both.
Yes. And angle PTB, angle between tangent PT and chord TB, is equal to angle A, angle in the alternate segment subtended by chord TB. That's Theorem 13 we just did.
Using the previous theorem.
Yeah.
So with angle P common and angle PDB, angle A, the triangles PT and PTB are similar by AA.
Correct, which gives proportional sides. PAPT equals PTPB.
Cross multiply. PAAPD equals PTT. There it is.
Exactly. It connects back nicely.
Wow. Okay. We've covered a lot of ground there. Tangents, radii, perpendicularity, tangents from a point, touching circles, intersecting chords, angles and alternate segments, second tangent theorem.
It's a really interconnected set of ideas. We saw how tangents and radii have that fundamental 90-degree relationship, which leads to rules about how many tangents you can draw and their symmetrical properties.
And how touching circles always have their centers and contact point lined up with simple distance formulas. Then those product rules for intersecting chords, PA times BB equals PC times PD, whether inside or out.
And the angle relationships, like the alternate segment theorem, and that final PA times PB equals PT squared rule, they all build on each other.
What stands out to you as maybe the most surprising or elegant takeaway from all this?
I think it's just how consistent and, well, elegant those product relationships are. PA, PB equals PC, PD for intersecting chords, and PA, EP equals PTT for the second tangent case. It feels like there's this underlying conservation principle at work with lengths and intersections. It's quite beautiful.
It really is. It shows this deep structure within seemingly simple circles and lines. So for you listening, we've unpacked these core geometric principles. But the question to maybe ponder is, how might these ideas actually show up, maybe unexpectedly, in the real world?
Yeah, think beyond just textbook diagrams. Where do you see tangents in action? Wheels on roads, gears meshing. What about intersecting paths or lines of sight? Could any of these geometric relationships, perpendicularity, equal lengths, those product rules offer some insight into how things work physically or visually?
It's something to keep an eye out for. Yeah. Look for circles, look for lines touching or crossing them, and see if you can spot these theorems playing out.
We hope this deep dive has given you a really solid grounding in these fascinating aspects of circle geometry. It certainly sets the stage for exploring even more complex and beautiful geometric ideas down the road.